Welcome to our channel where we talk about the core knowledge needed in various specialization within the field of traffic operations. Majority of the content in this video is written by Professor Jiangling Wu. My name is Amit Kumar Singh. I am a licensed engineer in the state of Texas. I received my bachelor's degree from IIT Bombay in India and my master's degree from UT Austin. Other contributors of this work include Prensu Singh, an artificial intelligence engineer, Nidhi Kumari, a computer science engineer, and Namrata Kumari, a data science engineer. Now let's get to the main content of this video. Before looking at the approaches that are needed for predictive safety analysis, I kind of wanted to mention that two best resources that are freely available to learn about the Highway Safety Manual and Predictive Safety Analysis is FHWA training on YouTube and ASTO webinar series on YouTube. So these two are very good resources. If you want to learn more in depth, then these two resources will give a very good background on the Highway Safety Manual. And the Highway Safety Manual is a kind of a must for a traffic operational engineer who works in safety. In previous videos, we have looked at descriptive safety analysis, which focuses on finding the crash pattern and historical crash data. Next, we will look at something called predictive safety analysis, where we can predict the safety aspect of the roadway elements. So predictive safety analysis is a data-driven safety approach, DDSA, that provide safety performance measures of existing as well as proposed roadway conditions. So using the predictive safety analysis, we can gauge how safe or unsafe proposed roadways are. So descriptive safety analysis cannot be applied for the proposed roadways because the historical data for the proposed roadways does not exist. However, predictive safety analysis enables us to look at proposed roadway or hypothetical roadways or different roadway configurations which does not exist. So data-driven safety analysis enables us to proactively identify safety issues and address them early in roadway projects. So when we are working on design and at different level of decision making, we can make these changes. Whereas the descriptive safety analysis and the next one, which is surrogate safety analysis, both are dependent on the existing or past crash data. So predictive safety analysis is mostly developed by FHWA, and the guideline which is used for predictive safety analysis is HSM, Highway Safety Manual, by ASTO. ASTO and FHWA guidelines. So Highway Safety Manual is the main guidelines that goes into predictive safety analysis, and we have two sections in predictive safety analysis. First, we will look at how the predictive safety analysis is used in practice, like an overview of it, and then we will go through one example for the predictive safety analysis for freeways. So for majority of times we apply the safety analysis mostly for freeways. Most of the freeways projects involve the predictive safety analysis. So predictive safety analysis can be used for different roadway types, whether it's two-lane roadway, multi-lane roadway, freeways, arterial. However, in practice is mostly applied to freeways and sometimes multi-lane highways. So we will look at a detail about the freeways, and the similar kind of approach is used for other roadway types. So that will be in section 4.2.2, which may be a separate video. So in 4.2.1 we will look at the overview on how to apply the predictive safety analysis. HSM is a very big guideline. We will not go in too much depth of Highway Safety Manual. We will only look at from the application side of things, so we'll not look at too much into theoretical side, mostly on the application side what we need to know. So the first step of predictive safety analysis is the roadway segmentation. Roadways are divided into homogeneous segments and intersections. So let's say we have a multi-lane highway here, and there are some intersections here, then we would go and divide them into homogeneous sections. So let's say section number 1, then we have intersection here, then we have section number 2, then we have intersection here uh, covering, and then we have segment number 3. So we divide the roadway into homogeneous sections, and the way homogeneous is defined is the roadway segment should have similar roadway characteristics and similar volumes. So the roadway and traffic characteristics that are considered for freeway segments. So if we are looking for freeway, then that would be area type. If area type changes between urban to rural, urban/rural, so if area type changes, then we will break the segment. Number of lane, when the number of lane changes, usually at merges and diverges, we would break the segment. Then lane width, the lane width changes by certain threshold we will look into, then we will break the segment. Shoulder width, median barrier, clear zone, ADT. ADT on freeways typically change near the ramps because freeways are control facilities, so whenever there are ramp, usually the ADT will change there, and presence of ramps. The next step is where majority of the highway safety manual work kicks in. So this is a equation, and most of the highway safety manual goes through each component of these equations. So the predicted number of crashes is calculated using the following equation. NP is the predicted number of crashes for a facility, and SPF is the safety performance function that is associated with particular facility type. So safety performance functions can be different for freeways. It has a different safety performance for freeways. Then we have, let's say, multi-lane highway, then 2-lane highway, then we have arterial segments, then we have intersections. So we have different safety performance functions and different factors which are defined in highway safety manual. Then we multiply them with crash modification factors using the attributes that are part of highway safety manual. So we are looking at CMF1, CMF2. These are different crash modification factor. These are core factors that affects the predicted number of crashes. So let's say safety performance functions gives us safety performance function are typically based on very basic attributes. One of them is length, another one which is typically there is ADT. So first, safety performance functions gives an approximate number of crashes, then these are adjusted based on HSM specific crash modification factor. So for example, let's say we are looking at clear zone, then clear zone, depending on the clear zone available, there may be safety performance function there, shoulder width, median width, type of barrier. All those factors have predefined formulas or the values within the highway safety manual. So these are crash modification factors from the highway safety manual. And then C local is the local calibration factor. So we'll discuss each one of them on the next page, but that's an overall equation to predict the number of crashes as a part of step 2. So the first one is NSF, which is the safety performance function, is typically, this is for freeway, so length multiplied by e to the power a, b and c. A, b, c are 3 coefficients. They can be calculated as a constant value or they can be an equation. So highway safety manual provides these coefficients. Typically, all the work we do for the predictive safety analysis is done through softwares. So there are 3 main softwares that are used. First one is IHSDM, which is freely available and developed by FHWA. So it's freely available and freely available for public use and developed by FHWA. Second one is iSATE. I think it was developed at TTI, but I may be wrong. So this is also a FHWA tool developed at iSATE is for freeway. It's an Excel spreadsheet to calculate to predict number of crashes for freeways. And then there are some new software which is HSS by MacTrans, which is highway safety software similar to highway capacity software. So most commonly in past we used to use ISAT, but now we heavily rely on IHSDM to do the predictive safety analysis. So we will discuss some of the things here, but majority of them are implemented through softwares. Here on the safety performance function, this is the functional form, and there are coefficients or equations that are available in highway safety manual, and IHSDM or one of all of these softwares have this coefficient inbuilt in them, so they can pick up the appropriate coefficients. So the functional form and coefficients of the safety performance functions are provided within HSM. SPFs are different for different roadway type and intersection. So safety performance function, this is a functional form for freeway, but it may be different for different roadway type. Let's say we are working for arterial, then the safety performance function would be different. So safety performance functions are different for different roadway type. Many state DOTs, let's call them local transportation agencies, so usually at state level, not at MP or county level, there may be some safety performance function that are developed. So if the local transportation agencies have developed safety performance functions, then safety performance function for local regions would be used. So this is very important. There are national safety performance function for entire US, which are given in highway safety manual, which are intended for entire US. However, many DOTs have developed their own safety performance functions, which looks similar to the national one. For example, FDOT has their own safety performance function for some of the facilities type, not all of them. Then there is Illinois DOT, they have their own safety performance function. So if the safety performance functions are available and they are as detailed as the national safety performance function, then we should be using the local agency safety performance functions. Typically when we say local agencies here, is mostly state DOTs, because safety performance functions takes a lot of research to develop. So it's usually developed by state DOTs. HSM based crash modification factors, which we were discussing here. So CMF1 to CMFI are HSM based crash modification factors. These are values or equations that are provided in HSM. CMF are typically only applied to certain proportion of crashes. So this is another important kind of thing to remember, that crash modification factors may apply to only certain part of crashes. So let's say we predicted the number of crashes to be 100, and now we are trying to multiply different CMF. Now the CMF1 may be applicable to, let's say, fixed object fatal injury crashes. So out of 100 crashes, we first need to figure out how many are fixed object fatal injury crashes, and then CMF1 may only apply to this proportion of crashes. Then CMF2 may apply to certain different proportion of crashes, or CMF3 may apply to the first one. So there are different crash modification factors. These crash modification factors are usually between I would say 10 to 30. So there are 10 to 30 different crash modification factors we are looking at for different facility type, and they apply to different segment or different part of the crashes. So first we need to split the crashes into different parts, and then we apply the crash modification factors onto them. So this is a very complex task to do manually, trying to figure out how to split these crashes into different proportion, and they do not necessarily need to sum up to one, because some may be relevant to, let's say fixed object fatal injury crashes, but some may be relevant to fixed object all crashes where fatal injury is already included. So they are not split, they are like subcategories of this full crashes. So some may have 80 crashes applicable to them, some may have 100 crashes applicable to them, some may have, like, let's say 10 crashes applicable to them. So maybe CMF1 is applicable to 100 crashes, maybe CMF2 is applicable to 80 crashes. and then we need to figure out under what category we are applying, and then we sum up based on that category. So it's kind of a complex uh, work here that is usually done within the software. So this is the part where which is kind of very difficult to do it manually, and usually softwares are used. So softwares like IHSDM, ICT, or highway safety software, these are used to perform these calculations, because it's a highly complex to split this into different proportion all the time for all the projects, and then apply crash modification on particular proportions or particular categories of crashes. The third one is a local calibration factor, and this is another important factor we have in highway safety or predictive safety analysis. So local calibration factors that are applied to safety performance functions here are developed usually by state DOTs. So first, why this is needed. So highway safety manual guidelines has been developed based on data from only few states within the US, using the crash data between 1985 to 2003. So first, these equations, which are safety performance functions and the crash modification factors, those are statistical equations, those are not mathematical equations, which means there is some uncertainty. Statistical equation, so there is some uncertainty or some error associated with them. Depending on how good the data is and how well the curve is fitting that data, the prediction may be accurate or maybe off. So when we are looking at the safety performance function, the underlying data plays a very important role, as well as the curve we are trying to fit. Since the data which is used for the safety performance functions were developed based on few states in the US, and using the past data which has become kind of outdated, so local calibration factors are typically recommended to improve the accuracy of the prediction. So regression-based safety performance function and CMF may not be suitable for local conditions due to variation in driving conditions across the US. Not only across the US, even within the states, between different cities, the driving behavior changes. So it's kind of important to calibrate the safety performance functions or the predictive analysis for the local region. It's better to calibrate them at MPO level, but usually as of now the calibration occurs at DOT level. So state DOTs develop this local calibration factor. Consultants do not go and try to figure out the local calibration factor. Usually it's done by research agencies. For example, for Texas it may be TTI who would develop these local calibration factors. So as a consultant, we don't go and look at similar facility and try to predict the local calibration factor. This comes from the state DOTs, and if in future if we are looking for more precise answer, then MPOs may develop their own safety performance functions. Therefore, the calibration of SPF in local conditions is recommended to improve the crash prediction model. Not only that, it's also said that the local calibration is usually the best way to improve the crash prediction, because the equations in the crash analysis are developed based on few states of data and historical data. So it's always better to use the local calibration. A local calibration factor is just a factor which is applied onto the overall performance function. So first, local agencies may have their own SPFs instead of the HSM SPF, and then we can use the local SPF. And if let's say local SPF is not there, then we can if the state DOT has developed some calibration factor, we can apply that calibration factor here. Similar to SPF, the distribution of severity and manner of collision within the highway safety manual is developed based on limited data sets. So not only this safety performance function and these equations, we also need to know the distribution of crashes. Distribution of crashes by manner of collision and distribution of crashes by crash severity. So this distribution of crashes is usually not developed for project, so we don't use the crash data for project to change the distribution of crashes. This is a typical distribution of crashes for that particular roadway type in the given region. So we are not looking to figure out the distribution of crashes based on our project. So this values needs to be a standard value for entire region that is usually developed by state DOTs. So if this data is available, even though this data is available for projects, we are not looking to calculate this table based on projects. We are looking for the state DOT guidelines which will give this distribution of crashes for particular roadway types. So if the local calibration factors are available, then we need to use the local calibration factor. Also, if the local distribution of crash severity and manner of collision for that particular roadway type is available, then we would use the local crash distribution, but not on project by project basis. We would use the local distribution of crashes based on the DOT guidelines or the DOT's research. Next step is to adjust the predicted number of crashes to local site conditions. So first we segmented our freeway into smaller segments. So let's say we segmented it into smaller segments. So for each of the segments we apply step 1 to 5. So in step 2 we predicted the total number of crashes using highway safety manual guidelines and local calibration factor. In step 2 we would try to adjust in step 3 we would see whether this numbers needs an adjustment. So in step 3, as we mentioned in step 2, these are all predictions, and depending on how accurate the prediction models are, our numbers may be off to reality. So step 3 is to adjust the predicted number of crashes based on local site conditions using something called EB method or Empirical-Bayes Method, which is mentioned here. However, step 3 is not used much in practice. So step 3 is kind of a important step theoretically, but is not used in practice because of the nature of projects. So we'll talk about what is step 3, how to use it, and then we will talk about why it is not used much in practice, or in majority of our work we will not use actually step 3. So let's look into what is step 3. Step 3 is the expected number of crashes. So first we had predicted number of crashes from previous step, so this came from step 2. Then we are trying to adjust the predicted number of crashes to calculate expected number of crashes based on something called dispersion parameter W. So this is actual number of crashes that is observed at the site. So it's well explained in this figure. So what happens is when we are predicting the number of crashes lies along a curve. So let's say the number of crashes predicted is this. However, based on and this is we are trying to predict the number of crashes for existing so that we can calibrate the model. So this is existing curve. However, we know from the past data that the number of crashes needs to be higher. So let's say we predicted the number of crashes to be 100, but in reality we know that the number of crashes are 150. So based on the dispersion parameter is obtained from highway safety manual and is an indication of how good, when the model was developed, how good the curve was fitted. So we can think of this dispersion parameter as standard deviation or variance when the model was built. So when the model was actually built, there were a lot of data set, and based on this data set there was a curve that was fitted, and which was kind of released to be used nationwide. So let's say this is highway safety manual curve, and there is a curve that is fitted, and we are going to use this SPF. This is a safety performance function curve Now, depending on when the research was done to develop the safety performance function, how good this model is fit is given by this W, which is the over dispersion parameter. We can think the over dispersion parameter uh, similar to standard deviation. So the higher the over dispersion parameter, K here is the over dispersion parameter. So W here is the weight that is assigned to the quality of prediction matter. So the uh, higher the over dispersion parameters, the lower the weight of the prediction. So if a model has more variance, or let's say a model has more over dispersion parameter value, which means the when the model was developed the variance was pretty high, or we can think like the model is not that good because the model is not fitting the curve properly. So we can think of K, which is over dispersion parameter, as an indicator of variance. So if the K is high, then we will give less weight to this prediction. So if the K is high, then we will give less weight to this prediction, and we will move closely to the observed value. But if the K value is low, then we will give more weight to prediction, and we will end up more closer to this prediction. So depending on the value of this over dispersion parameter, which we can obtain from highway safety manual, which kind of indicates how good the model is when the model were developed during research, we would determine how much we want to move away from the prediction. So if our prediction is 100 and observed is 150, and let's say we are very confident that our prediction model was good, then we might end up with a number like 110 or 105. Or if the over dispersion parameter was very high, which means our model when it was developed was not that good, then we might end up with a number, let's say 140. So the final number always lies between the predicted number and observed number, and depending on how good the models were when they were developed, we'll move away from the prediction towards the observed. So this is step 3 in a nutshell, which is called Empirical-Bayes Method. Now this Empirical-Bayes Method has been applied on the existing. If we want to apply it for the future, let's say in existing there are 150 crashes. So this is observed existing, but total number of predicted crashes were 100 predicted but for existing. So for future, if we are predicting, let's say 200 crashes, then we know that we are underestimating the number of crashes, then we will bump this up to 300 crashes. So that's in a nutshell on how this Empirical-Bayes method is applied for future. So first we figure out how to apply it for the existing and figure out what is the expected number of crashes. Then based on the expected number of crashes, we adjust the future. So this is observed, and this is not predicted, this is expected number of crashes. So in this example, let's say our expected number of crashes lies here and is 120. So I'll change this to 120 expected number of crashes. So in future, let's say if we have 200 crashes, then we will change it to 300 here. So this is a ratio method, is pretty simple. As another example, let's say we observe 2000 crashes in existing, but we expected number of crashes in existing, which we calculated using this adjustment, is 3000. Then in future, so this is predicted existing, this is expected existing. If we are predicting in future, let's say 3000, let's say 4000 crashes, then we know that we need to bump up this number to in this ratio. So it would be, so this is double, so this would get double, so it will be 6000 crashes expected for future. So So this is predicted future and this is expected future. So this is how we can adjust the future models to match the empirical base which we calibrated in existing. However, it's a big however, this model is typically not used in practice. All these things are done for safety studies and mostly for to compare before and after studies, but it's usually not done in practice. The limitation is written here. Please note that the built roadway conditions usually differ significantly for existing roadway conditions, such that the observed number of crashes and empirical Bayes method is not used. So one of the conditions of using the empirical Bayes method is used to adjust the future crashes. If the empirical Bayes method is used to adjust the future crashes if the roadway conditions remains the same between existing and future. So we can use this formula only if the roadway condition remains the same between existing and future. If the roadway condition changes between existing and future, this formula is not applicable anymore, and since we are not using the expected crashes, this is also not used. So there are several state guidelines, for example Florida Department of Transportation guidelines, Oregon Department of Transportation, and Ohio Department of Transportation. There are many state guidelines that outlines this limitation of empirical Bayes method, that when the roadway changes significantly, for example if we are widening the roadway and adding one lane, or if we are changing the center line alignment, which is majority of projects. In majority of roadway projects we work in practice, the roadway alignment changes significantly. When the roadway alignment changes significantly based on different guidelines, we should not be using EB method. So is in step 3, which is under safety predictive safety analysis, EB method is used. Those are mostly used for before and after studies. Before and after studies, usually for the research papers. After studies, so it's kind of important to know what the empirical Bayes method is and how it's used, but it's also very important to know that it's mostly not used for roadway projects. So not used for roadway, mostly not used for roadway projects, so it's very important to understand this. And the last one is to adjust the expected number of crashes based on crash modification factors that are not included in highway safety manual. After step 3 of EB analysis, which is typically not used in practice, what we have is the predicted number of crashes, and if the EB analysis is used, then we will have expected number of crashes. So after step 2 and 3, what we have is, let's say, predicted or expected number of crashes. So number of crashes predicted, we have the number of crashes predicted for existing conditions as well as future conditions. So in future we have it for no build and several build alternatives. Step 4 is to adjust the expected number of crashes or predicted number of crashes depending on whether step 3 is used or not. Number of crashes based on CMF that are not included within highway safety manual. So there are a lot of CMFs that are not included in highway safety manual. So here in this equation we looked at some of the CMFs that are included in highway safety manual, but we may be looking at some CMF that are not included in highway safety manual. Let's say the lighting conditions are not included, and we are doing some improvement which is out of highway safety manual, then we need to figure out a way to adjust our number of predicted crashes to adjust for those countermeasures. So if some of the countermeasures or some of the attributes of roadway or different conditions are not included within highway safety manual, let's say there is a new campaign which looks into drunk driving. So there is a new campaign that drunk driving is not good, and we want to include some kind of benefit because of the new things that are going on. So if there are crash modification factors that are available and those are of high quality crash modification factor, we may apply those for our projects. So the one of the best resource to find the crash modification factor is CMF Clearinghouse website. So we will look at this website. Every traffic or safety engineer must know about this website. Is CMF Clearinghouse, which is maintained by FHWA. It's a database of different countermeasures that we can apply on roadway, and the effect of those countermeasures on reducing either the total number of crashes or certain category of crashes. So this is one of the best resources to apply crash modification factors after the predictive analysis is done. When we are working on descriptive safety analysis and not predictive safety analysis, we can still use the crash modification factor which are available on FHWA CMF Clearing website. So we will have a look at how the website looks like, what are some of the features of this website, and also which CMF to apply. So once we search for certain CMF, there can be multiple CMF that can range let's say 50% different from each other. So we'll look at how to figure out which CMF to apply. So we have the predicted number of crashes, and then in step 4 we multiply them with the certain CMFs that are not available within highway safety manual. One important point to remember about the CMF is typically multiple external CMFs are needed to be applied for project. So if the effect of countermeasures are independent of each other, then all CMFs can be multiplied by each other to calculate effective CMF. So if we have predicted number of crashes, and let's say we have 5 independent crash modification factor. So if we are looking at 5 solutions that are independent of each other, so we have CMF1, then we can multiply CMF2 and so on. So multiplied by CMF5. If these CMFs or the countermeasures and the effect of those countermeasures are independent of each other, then we can multiply all the CMFs together onto the predictive number of crashes to calculate a revised predictive number of crashes. Let's call it N dash. However, many times some of the CMFs are related to each other. So let's say we are proposing 2 countermeasures that are related to each other, or those are gonna affect the similar kind of crashes. Then engineering judgment should be used to figure out a way to calculate the combined effect of multiple factors. So if the countermeasures are kind of related to each other and they are not independent, then we have to look at them on case by case basis. So typically we encounter this in practice a lot, and there is no direct answer to this question on how to combine them together. There are some guidance or some webinars around this, but there is no clear answer to how to combine the countermeasures if they are related to each other. So an engineering judgment is needed when the countermeasures are related to each other. We will look at CMF Clearinghouse website towards the end of this video. And the last step is to convert these safety benefits into monetary value. So each crash type based on severity level can be converted into equivalent economic cost using the values either provided in Highway Safety Manual or National Safety Council website, which maintains yearly cost of different motor vehicle crashes severity, motor vehicle crashes injuries. So let's say this table provides a sample economic cost. Let's say if we are looking at fatal injury, there are 2 kind of cost. One is sample average economic cost, which is the direct cost related to a crash, which includes the wages and productivity loss, medical expenses, administrative expenses, motor vehicle damage, and employers insured cost. So this is the direct cost that is related to a crash. And then we have something called comprehensive cost, which also looks at loss of quality of life. So let's say if somebody is severely injured and he loses the function of his or her leg, then there is a reduced value in the quality of life. So the quality of life the person is going to live after the crash is not going to be the same, even with the all the direct damages. So if we include the quality of life factor, then we have sample comprehensive cost. For most of the traffic analysis, we typically use sample comprehensive cost. Sample comprehensive cost on an average is 10 times of regular economic cost. So what we have is we have existing, then we have no build and B, then we have different build alternatives, build 1, build 2, build 3. Let's say we have 3 build alternatives. So we will figure out the economic cost related to no build, economic cost related to total number of crashes related to no build, then economic cost related to total number of crashes related to build 1, then build alternative 2 and build alternative 3, and then we will compare and subtract them out to figure out the total cost saving when we are building an alternative. So the cost saving in terms of safety for build 1 will be the total economic cost. Let's say the economic cost for build 1 is 1 million, and based on the number of crashes, total economic cost or total economic loss is 2 millions. Then the benefit of building alternative 1 from safety perspective is 1 million. That's the difference between no build and build alternative cost. Now let's look at the website of CMF Clearinghouse, which is maintained by FHWA, and then let's look at how to figure out the crash modification factors. This is the FHWA CMF Clearinghouse website. Here we can find the countermeasures and the crash modification factors that are related to countermeasures. Also, there are additional resources that we can use for the conducting safety analysis. So let's say we are trying to apply rumble strips on multi-lane highway in a rural area. So I'll type here rumble stripes, hit enter. So here I will find a lot of crash modification factors. Now we need to find the appropriate category of the crash modification we want to use. So within a single crash modification factor, here we can find the actual crash modification factor which we can use. Then quality of the research. So on this website gives different star values. So 5 star is high quality, so we typically like to go for 4 or above at least for the for projects. And then for what kind of crashes this crash modification factor is applied. So this 0.53 is applied to fatal and serious injury crashes only. So let's say we are interested in a rural area, so we'll select different filters here. And in HSM, so if we are looking for crash modification factor that are part of HSM, let's say we are working on descriptive analysis and not the predictive analysis, and we want to apply crash modification factors without doing predictive model, then we can use some of the crash modification factors that are available in HSM. HSM is considered the highest quality in terms of crash modification factor. So if we are working on a project and not using the HSM, then we can select the HSM crash modification factor. So only included in HSM 13. So if I click here, filter results, then these are the crash modification factor that are included in HSM that usually have very high quality associated with them. So if we are looking to install center line rumble strip, then these are crash modification factors we can use. If we are looking at shoulder rumble strips, so let's say continuous mild in shoulders and there is rolled in shoulders rumble strip, then these are different crash modification factors we can use. Uh, so in safety analysis, what we are looking to do is we are trying to go to CMF Clearinghouse website. We are looking at certain countermeasures. We'll type those countermeasures and then do some research to figure out which countermeasures to use, what kind of ratings they have. Typically, we try to go for 4 or above rating if we can, and if we are not working with HSM, then we try to use the HSM compatible crash modification factors. Here there are some additional resources. It gives the safety performance functions that has been developed by different local state agencies. First one is guidance on how to develop SPF, and then select state selected CMF. There is highway safety manual. There are other resources we can look at. So that's the kind of general background on the CMF clearinghouse. Is kind of important to know if we are working on safety project about this website. This is our to-go website to calculate the crash modification factors. Also, some latest research are always updated on this website, so it's a pretty good website to look at from time to time. That's all we have under the overview of predictive safety analysis. In the next videos, we will look at how we can apply some of this idea of predictive safety analysis for freeways. So what kind of input that goes within the freeway, how do we segment them, what are different factors that goes behind the HSM side of freeway, and some of the tips and tricks we can use for performing the predictive safety analysis for freeways. The same logic we are going to discuss for freeways applies to multi-lane highway intersections and other roadway types as well. However, freeways are what we frequently use in practice, so we will look through one complete we can say one complete application of predictive safety analysis for freeway, and for other ones is kind of similar, so it's more about learning the other ones. So other roadway types are not that frequently used in the world of predictive analysis. Mostly freeways are where most of the predictive analysis are used for, mostly the roadway design projects. So I will see you in the next video, and we will discuss the application of predictive safety analysis for freeways. Thank you.